This is Module 6, Inductive Reasoning. You have to define what inductive reasoning is. And all inductive reasoning is, it's the process you observe data, recognizing patterns, and making generalizations about those patterns. And the generalizations usually lead to a conjecture. And all a conjecture is, it's a generalization made from using inductive reasoning. So again, inductive reasoning, the main word to kind of look at is patterns. You're looking at something and you're trying to see what the pattern is within that set of data. So we have something that's called a counterexample. So a specific a case for which a conjecture is false. Counter meaning against the example. So find a counterexample to prove the following statement is false. Well, if I make the statement, the generalized statement of all apples are red, somebody can come across and make a counterexample, and I can say that, well, we have green apples, we have yellow apples. So automatically that statement makes my conjecture false. So we call that as a counterexample. In this, we have a scientist dips a platinum wire into a solution containing salt, or sodium chloride, passes the wire over a flame, and observes that it produces an orange-yellow flame. So, the observation is that we produce an orange-yellow flame. She does this with many other solutions that contain salt, finding they all produce, again, an orange-yellow flame. Make a conjecture based off her findings. Well, if I have done that with many different salts, I can make the conjecture that sodium chloride, or salt, produces an orange-yellow flame. That's my conjecture, based off of the patterns that I've seen from this experiment. Another way of using inductive reasoning, looking at patterns, is through numbers. And a lot of people do this. They ask questions like these in SATs, ACTs. So you see this quite often. But using inductive reasoning, we look at the set of numbers here. The set of numbers, we have 2, 4, 7, and 11. So it says, use inductive reasoning to find the next two terms. So we have to find the next two terms in each sequence and explain the pattern used. So explanation in mathematics usually just kind of relates to notating what's going on. So, for example, I look at this and I say, okay, well, going from 2 to 4, I'm adding 2. Going from 4 to 7, I add 3. So no pattern yet. Going from 7 to 11, I add 4. Okay, so automatically I'm seeing here, all I'm doing is I'm adding 1 to my previous amount and increasing it. So if I added 2 here, 3 here, 4 here, what do you think you're going to do for the next one? Yeah, you're going to add 5 here. So adding 5 gives you 16. Now let's add 6. That gives you 22. So those are the next two numbers. My explanation, my explain, was shown here. You don't have to write it in words. If you want to, you can, but I'm showing it here. That's my explanation in mathematics. So, okay. What about this one, B? We have 1/6, 1/3, 1/2, and 2/3. This one's actually a little more hidden, and in which case you can see that patterns can be very obvious, like in A, or they can be hidden, like in B. So we have 1/6, we have 1/3. So I'm looking, the top's not changing, except for here. It changes to 2. So, okay, there's no pattern there. What about the bottom? Well, I decrease by 3, then I decrease by 1, but then I increase by 1. Okay, so there's no pattern there. What about the fraction themselves? So if I look at what the value for each one of the fractions are, okay, well, one of the tools that you used in elementary school is how to manipulate fractions. Well, okay, let's see, we have 1/6. If I have a common denominator, 6 here, well, 1/3, if I multiply the top and the bottom of 1/3, I get 2/6. Okay, so I got a common denominator here. That's nice. What about the next one? I multiply the top and bottom by 3, and I'll get 3/6. Okay, now I'm starting to see a pattern. I add 1 to the numerator, to the top. And if that's the case, then I can continue it. Let's see if it actually holds true for this one. So I'm going to multiply the top and bottom by 2. So I get 4/6. And again, my pattern holds true. I'm adding 1 to the numerator. So I'm going to do the exact same thing. Add 1 to the numerator, I get 5/6. Add 1 to the numerator, and I get 6/6, which actually can be reduced to 1. But you can keep it as 6/6 as well. So the denominator is the same throughout, and you're just adding 1 to the numerator. But looking at B, the pattern is hidden. You have to kind of pull it out, and that is, for a lot of cases within a pattern, trying to find out what the pattern is. Okay, so we have, looking at the graph here, we have which conjecture could a high school athletic director make based on the graph at the right? Okay, so we have A. Let's see, more boys play soccer than girls. Well, let's look at this. We have, this is girls' registration. Well, it has nothing to do with guys. More boys play soccer than girls. So we have nothing that's dealing with guys. So A is out. All right, let's say more girls are playing soccer today than in 1995. Well, looking at this, I see a pattern that this entire data set is increasing. So if the data set is increasing, I could say, okay, more girls playing soccer today than in 1995. Yeah, I could probably say that. I think B is probably it. But let's look and see what C says. More people are playing soccer today in the past because the 1994 World Cup games were held in the United States. Even though that's interesting, that has absolutely nothing to do with the data set that's here. So I think C's gone. I don't think you can make a case for it either. What about D? The number of girls playing soccer was more in 1995 than in 2001. Well, if you look at 2001 versus 1995, 1995 is here. 2001, that's about here. Okay, and they're saying the number of girls playing soccer was more in 1995. I'm going to say no with that one because this guy here looks to be less than this guy here, not more. So D is gone. So we just kind of went through and looked at the pattern, showed the pattern was increasing, so we know B is the correct answer.